We're live.
You didn't have those the other days, the countdown.
It did, but I didn't make a big deal out of it.
Yeah. Contagious.
Compared to some of the software we've got, Camtasia is really easy to use, and it's kind of cool.
They make video editing really easy too.
The version I have makes video editing very easy. The one that most teachers have is Camtasia Relay. You just get what you get. You know, you can't edit it afterwards.
I've got Camtasia on my computer.
So if I say something really offensive, I can go back and edit it out, which for me is a really good idea. Especially when I had Maury in the class. Okay, we got through the first couple of examples, and sorry about this. I'm also going to need the icon strip.
Couldn't you use the one on the board?
It doesn't work. They've replaced it and everything. It just will not function. It refuses. So now I need this little box off to the side. I know I sound like I'm whining, but you know, it would be really helpful if it worked.
Is it like outside of the cameras or the sensors?
I don't think we finished the second example.
Oh, we didn't finish the second example. Okay, my apologies. Back up just a sec.
We have to go to line.
Okay, so on this one here, balls thrown at 14.1 meters per second, 45 degrees below horizontal. Someone located 30 meters away along the line of the path starts to run just as the ball is thrown. How fast and in what direction must the person run to catch the ball at the same level in which it was thrown? Okay, the bell rang. That's why I didn't give you any problems yet. I was wondering why I didn't give you any problems. So there we go. Okay, so yesterday, you'll have to help me out how far we got, because we've got this ball thrown at 45 degrees. Wah. It lands over here somewhere, and we determined that we had to find delta x first. And we'll figure out, you know, what the person has to do, but let's calculate delta x first. Here's v naught, the initial velocity, which we're going to break down into components. Here's our angle theta. This is v naught cosine theta. This is recap, by the way. This is v naught sine theta. We have a launch velocity of 14.1 meters per second. We have a launch angle of 45 degrees. Okay, so we can figure out the y and the x initial velocities. Then yesterday, what I did was break it into two sections, delta x and delta y. Generally, not always, remember there are three kinematics formulas which work when you have a constant acceleration. The one we use most often is the Dragon equation. Okay. However, the other two are still in play. So every now and then they'll ask a weird question, and don't limit yourself to that equation. You might need to know the final velocity after just moved a certain distance and not know the time, or something like that. It's rare, but it happens. Okay, so what we did yesterday was we said, hey, you know what? This v naught in the x direction, we have to replace it with v naught cosine theta for this case. Because if we're only looking at the x direction velocity, or the x direction motion, we know it's constant velocity. So the zero acceleration, our equation that should be in your notes right now, is v naught cosine theta delta t. Any questions about that? Are you okay with that equation? Why we left off the a? No acceleration in the x direction, and the initial velocity is not v naught in the x direction. V naught is at some angle. We can't deal with that. Okay, delta y. Let's see if I can move this a little bit. Delta y is v naught sine theta, because that's the initial velocity in the y direction, delta t minus 1/2 g delta t squared. Did I solve this guy yet for time? That's where we left off. That's what I was thinking. Okay, so if I'd like to know what delta x is, I need to know three things. The initial velocity, got it. The angle of launch, got it. time of flight. Oops, don't have it. So we walk over to the delta y side, because that really controls the time of flight, and say to ourselves, okay, in order to find the time of flight, I need to know the angle. Got it? I need to know g. Got it? I need to know v naught. Got it? I need to know delta y. What's delta y? 0. Now that sounds really bizarre, but what's the y-coordinate of the ball right there? What's the y-coordinate of the ball right there when it hits? 0. What's 0 minus 0? So if you go with the ruthless definition of the change in y, it's 0. Remember, it's from where you start to where you end. We don't care how you get there. That's the displacement. So this is 0 for this case. So all I have to do now is solve that thing for time. Okay? So you've done this before in math class, except this looks really weird. I'm going to factor out a t, delta t, and get v naught sine theta minus 1/2 g delta t. So really I'm going to do some factoring and then check the two factors to see when I can make this function equal to 0. So one way to make this function equal to 0 is say, oh, delta t equals 0. Okay, that's one solution. If you set time equal to 0, the thing is at ground level. Oh, yeah, that's like the trivial solution, right? Of course it's at ground level at t equals 0. We knew that. The other solution is when this thing in parentheses equals 0. And this thing in parentheses equals 0 at when v naught sine theta equals 1/2 g delta t. Okay? Don't get all tied up with all the symbols. This number here equals this number here. Then that parenthesis chunk turns to 0. So when we set them equal to each other and solve for t, we get t delta t equals 2 v naught sine theta over g. Dun, da, da, da. Now I kind of ran out of room for punching numbers in. Sorry, Amanda. Punch v naught in for, let's see, 14.1 in for v naught. Punch 45 degrees in for theta. Divide by g and figure out the time of flight. So 2 times 14.1 meters per second multiplied by the sine of 45. Divide by 9.80 meters per second squared. And someone out there has their calculator and nimble fingers, and they're telling me the answer is going to be 2.03, says Jake. .03 seconds. That was the piece of the puzzle we were missing. Now we can find delta x. The delta x is going to be 14.1 meters per second times the cosine of 45 degrees. I can just fit it all in there. Times the time. I'll cheat, put a little arrow there. Okay, so 14.1 times the cosine of 45 times 2.03. What you got? 20.3. So just over 20 meters. So this is 20.3 meters. Our dude is standing out here somewhere. He's too far away. He's 30 meters away. So as soon as he throws the ball, he makes a quick mental estimate of where it's going to land, and he starts running toward the thrower. How fast does he have to move in order to make it? On average. What's his average velocity if he catches the ball? 4.78. What'd you say? 4.78. Is that doable? Can a person run at 4.78 meters per second? So it's like half this, the length of this room in 1 second. You'd have to be moving, but it's within the realm of human beings anyway. We're not asking him to like be a car. He'd be a pro athlete, yeah. So what we're going to do is we're going to say, okay, his velocity is 30 minus 20.3, which is going to be 9.7 meters. And he has to do it in a maximum time of 2.03 seconds. Okay? And what'd you say? It was 4.78?
4.77.
4.77. Okay.
I got 4.7. Yeah, it's 4.7.
Oh, is it? Okay.
It depends how early you round.
Come on.
Depends on where you're around. All right. That's why you show your work, so I know what you're doing. Okay. So I could have assigned one of these last year. There's a little wrinkle with that last calculation. What do you do? But it's not that bad. Now what I'd like to do is get into a couple of examples that I wouldn't have assigned last year. Okay? So, erase and move forward. Woo! All right. The magic whiteboard seems to be in a good mood today. Okay. Daredevil motorcyclist. I think I did have one of these last year as kind of an extra credit-y kind of thing. Daredevil motorcyclist plans to jump across a 60-meter gorge. He takes off on a 15-degree ramp. What's the minimum speed does he require if the two sides of the gorge are at the same level? So, we got a ramp and a ramp, let's say, and you got to try to draw the motorcycle and the guy because that's the fun part. And so he launches and he goes, just makes it. Okay? So once again, I'm going to assume he launches and lands at the same level. Makes our lives a little simpler. Delta X, 60 meters. Angle of the initial velocity is the same as the angle of the ramp. 15 degrees, which is kind of a shallow ramp now that I think about the problem. Okay. I'm trying to figure out how I'm going to get all this on the whiteboard here. He's going to die.
15 degrees.
Yeah. That wasn't a very well set up stunt. Okay. Now you make my patented T. You don't have to use the T. I mean, they don't expect you on the AP physics test to use the T. I just like the T because it separates physically the two types of motion, the X motion and the Y motion. So that's my invention. Don't, I'm going to patent that or copyright it at some point. The Evely projectile T. That doesn't sound good. Okay, so again, shades of the dragon equation. You saw this in the last problem. Delta X equals V naught cosine theta. Delta T for motion on the x-axis. Delta Y equals V naught sine theta. Delta T minus 1/2 G delta T squared on the x-axis. Okay, and I explained earlier where those equations came from. Just going to make the assumption that you're going to agree with them now. What are we trying to find? Okay. No problem. We're looking for V naught, right? How fast does he have to leave the ramp? So when he looks down at his speedometer, what should it read just as he leaves the ramp? And if it's anything less than that, he's going to say his prayers as he goes over because he's not going to make it, right? He'll probably say his prayers anyway. I would. But again, I wouldn't be doing this because, I got a family to think of. Okay, so delta X, we know it. V naught, we're trying to find it. Theta, we know it. Delta T, dang it, Unknown. Other side, delta y. Do we know it?
Yeah.
Darn tootin' we know it. In this case, it's 0. V naught we're trying to find. Theta we know. Delta t we don't know. So both of these equations are unsolvable. They both contain two unknowns. But, well, if you have one equation and two unknowns, what do they call that in mathematics? A problem? Yeah. Well, a problem is, a problem is usually solvable. But if you have one equation and two unknowns, the technical term in math is you're screwed. But if you have two independent equations and two unknowns, mathematicians go, woo! I can solve that. Okay. So what do you want to do?
Solve it.
Yes, we want to solve it, but what route are we going to take?
Couldn't you?
Plug the equations equal V naught and set equal to each other.
Okay, great suggestion. So if I solve this guy for V naught, and I solve this guy for V naught, and then click the two equations together, how am I going to find V naught? I just eliminated it.
You could.
You see what I'm saying? Okay, one method would be find the time, because that would be our other unknown, and then plug it back into one of the equations. That will work. I'm here to tell you it's kind of the long way around, but the long way around is okay. Because a lot of times on these problems, I take the long way around because it makes more sense to me. But I'm going to show you a little quicker way. Yes, ma'am?
Couldn't you do delta x and make that delta t equal to v naught cosine, or delta x divided by v naught cosine, and then plug that in for delta t and another one?
Oh, so I could take the x equation, solve it for t,
And then plug
take
it
that expression, stick it in for t here and t here.
Mhm.
Excellent. That would work. And I could do it in one swell foop that way. I'm going to show you a different way because there's nothing wrong with what you said, but this is a simpler equation right here. The delta x equation is slightly simpler. So remember in the last problem, I'm going to skip some steps here. Remember in the last problem, when we solved this, we got delta t equals v naught sine theta over g. Because if you go this direction, you only have to plug it in once.
Isn't that 2 V?
You're right. I beg your pardon. Whoa. See? More coffee. So if I take that expression for delta t and stick it into this equation, it's a little simpler route to go. Now, the reason I know that is because I've done these problems before and I've got lots of experience. If you take a different route, like the one Mr. McGraw said or the one Ms. DeYoung said, just fine. Okay? It's going to take you a little longer. The longer it takes, the more chance that you're going to make an algebra mistake, at least for me anyway. So go ahead and finish it up. You're going to get kind of a mess here for a second. Oops, let's see. I'm going to show my skill at this board. I need to erase this. There we go. I don't think it's my skill. I think the board is just in a good mood this morning. All right. So I got v naught cosine theta times 2 v naught sine theta over g. And that's a mess if you've ever seen one. I'm going to continue up here. X equals 2 v naught squared sine theta cosine theta over g, just to clean it up a little. So v naught is the square root of delta xg over 2 sine theta cosine theta. Okay, check that out. Make sure I did it right. It's still 0 hour, so my brain is waking up. Morning, Maddie.
Hi.
How you doing?
Good.
Excellent. I didn't mention this, but you're always welcome in the other class's 0 hour. So if you ever have the need or the urge to come in to the Tuesday 0 hour, or in Maddie's case, the Thursday 0 hour, feel free. Okay. Slide your numbers in. We've got a 60-meter gorge. That's a weird word. Times 9.80 meters per second squared. On the bottom, we have 2 times the sine of 15 times the cosine of 15. And I don't have my notes open, so I'm sure someone out there will get it before I... Oh, I do have my notes open. Here we are. I just never use them. Okay. How you doing? What'd you get?
He's talking to me.
Oh, he's punching? Okay.
34.3.
That's what I got. 34.3 meters per second. If we go with 2 sig figs, because of the 15 degrees, I got 34 meters a second. Okay. Now, we use this crazy metric system that nobody really understands because we are not metric people, we're English unit people. But the rule of thumb that I use is 15 meters per second is about 35 miles an hour. I just keep that in the back of my head. I don't use it for calculation or anything. I just use it for estimation. So if 15 miles per hour is 35, I beg your pardon, I said it backwards. 35 miles per hour is about 15 meters per second. This guy's doing like 70. Probably more than 70 because he's doing 34. So it's a reasonable answer. On a motorcycle, you can definitely do 70. You could do 100 if you wanted to. So could he do this? Yeah. It's in the realm of possibility. Why might he want to go a little more than 34? What's really going to happen in the real world? This is a physics problem. In the real world, what else do you have going on? Air resistance. Lots of air resistance, especially when you're moving at 70 miles an hour. I mean, you've got the wind in your face, right? So if he goes exactly 34 in real life, he's not going to make it. So instead of doing 75, maybe he wants to do 80 or 90 just to be sure he's going to end up somewhere on that other ramp. Okay? So you got to keep in mind, I mean, my job is to teach you how to do physics problems because that's what's on the AP test. But you got to keep in mind, a lot of these physics problems don't contain complete reality. All right? They're cool. I mean, the fact that we can come up with this number and we have a good baseline, of how fast he should go, that's valuable. But we have to remember, in the real world, it's not exactly 15. It's 15 plus or minus 2 degrees. There's air resistance. So that's why we do labs, just to show you that the real world kicks in and there are factors we have to worry about. Last one here on the projectile side. We have time for one more.
So will we be working on the problems in class, or will we do something?
A little of both, I'm hoping. I'm hoping to get some physics in second hour and then give you a little time because I don't want the assignment to get too big.
Okay.
I'm going to do my best. I'm not perfect, but I'm going to do my best. All right. Okay. A plane dives at 37 degrees to the horizontal and releases a quote-unquote package at an altitude of 200 meters. The load's in the air for 4 seconds. Find the speed of the plane and the horizontal distance traveled by the package after it's released. Okay. We didn't do that one like this last year because it's a little freaky, but take a look a sec. By the way, most textbooks nowadays wouldn't do this. They'd say it's a package of relief supplies for people stranded here on the Arctic tundra. This book's old enough where they just come clean and say, yeah, it's a bomb. Okay? We're trying to blow something up. Now, when it was released over here, it was moving at some angle below the horizontal. And that's V naught. Okay? The speed of the plane when it's released and the speed of the package when it's released are the same. So we're seeing, the picture shows us after the release, but when it was released, the package and the plane obviously had the same velocity. And that velocity has two parts, just like we've been saying. V naught cosine theta. Whoops, there we go. And V naught sine theta. Now, I got to draw it in. What's different about my V naught sine theta than was before? It's negative. Yeah, it's down. So I have to put a negative sign on this. Kind of ran out of room over there. Sorry, Amanda. There's a negative V naught sine theta for the initial velocity in the y direction. And so think of it this way. The plane is taking this bomb and throwing it to the right, while at the same time whipping it toward the ground. It's giving an initial downward velocity. So if you have like a ball on a bridge, you're standing on a bridge and you throw a rock in, you could throw it, out or up, or you could whip it down. You could say, oh, there's a fish down there, I want to nail that thing. Whoa! Now you wouldn't really do that because you're environmentalists and nice people. But you could give it a downward initial velocity, and that's going to change everything, right? Once you release the ball, though, okay, I've got this eraser, and I throw it downward. Once it's out of my hand, once I'm no longer touching it, what's its acceleration? Downward. Yeah, it's still, okay, I can't affect the acceleration due to gravity. I'm powerful, but I'm not that powerful. I can affect it when it's in my hand, but as soon as it leaves my hand, only thing acting on is gravity. Okay? So there's really nothing weird going on here. I'm not sure how I'm going to do this on the board, Amanda. I'm going to do my best. Let's see. 0 hour goes to 45, so we're like 1 minute away, aren't we? Okay. What do you have first hour? Espanol. So during Espanol, I want you to think about this, how we would do this. It's not that different from what we've done before. All right, we'll finish this up. Second hour. You get me twice today. Aren't you lucky? Oh, good question. We'd like to know how fast it was moving. What's V naught at release point? Okay? So I'm going to pause this crazy thing.
Yeah.
Okay. So what are the chances I am recording again? Oh, look at that. I'm recording.
You have your mic already and set?
Yep. Ready to rock and roll. Okay. So probably should get going, otherwise Sassy's going to say the video's too long.
It's gonna be extra long today.
Yep, with 0 hour. I was going to make 2 videos, and then I saw the pause button and thought, what the heck? Let's make one giant monster video out of it. It probably won't fit on YouTube or something. But, All right. So you had a good day in AP Chem?
Yeah, I did actually.
Things were good.
We get home, I fell asleep and maybe.
Wait,
No.
you finished first hour now?
For me, yeah.
No falling asleep in AP.
Take it out.
No, I played a game on my phone.
You naughty kid.
Well, he was like, here's the homework, and I finished the homework, so then I was like, what do I do now? And he's like, I don't care. So then I just went on my phone.
Okay, quick recap. Plane diving at 37 degrees. I have to redraw my stuff. Uh-oh. Where is the pen of goodness and light here? Ah, there it is, underneath all my stuff. Nope, that's the cap. There's the pen. Okay. Whew. Let's Scared me. Okay, let's see if we can make this work. Is it still connected? Oh my gosh, I can't believe Granville Technology is working this well. All right, so go back, hit the draw layer. Look at that. Oh my gosh, it's still there. I'm having like a small heart attack here right now. Everything's working beautifully. Okay, so like we said, the velocity is at an angle down toward the ground. He's kind of doing a dive bombing run. And we've got a negative initial velocity in the y direction. And we'd like to know how fast is the plane moving, and that is, how fast was the plane when the package was released, and what horizontal distance does it travel after release? Yes, sir?
Can we turn off just these cameras?
Oh, yeah. Let's turn off some lights. That'll probably help Amanda, too, if I turn off a couple lights. There. Hope that looks better, Amanda. I can just hear what she's saying right now. Okay. So how are we going to do this? It says, okay, theta, let's do our givens here. Whenever you're wondering what to do, write down your givens. That's 37 degrees. Delta y, what's delta y? Nah, it's not 200 meters. Negative 200 meters. It's okay, you can call me names under your breath. I've heard them all. Okay, gosh, I don't know what to do. So I need a little room to do this too, so I'm going to mess up my diagram. Okay, so our equations are, remember from the past ones, delta x equals v naught cosine theta delta t. Now you think the pen really isn't working anymore, or?
Is the light
Just throw the pen.
Oh, the light came back on, and so it should be connected again. Let's see. Yes. So v naught cosine theta delta t. Okay? Now, remember where this comes from. It comes from the dragon equation, right? V naught delta t plus 1/2 a delta t squared. So when I do my delta y, this has got to be the initial velocity in the y direction. Okay, so we tend to memorize a few things and then use them. However, we have to be careful now. What is v naught in the y direction this time? It's negative. It's different from before. So we're going to have to kind of like be thinking when we write this down. This is negative v naught sine theta delta t minus 1/2 g delta t squared. Can you read that okay? I'm trying to do it on the whiteboard so it comes up in the recording, but you know.
Good night.
Okay, so we're looking for the speed of the plane. Question. Delta x? We don't know it. V naught? That's what we're looking for, right? Theta, 37 degrees. Delta t, 4 seconds. So I don't know delta x or v naught, but I do know theta and delta t. All right, so this equation, very difficult to solve. This one over here, do I know delta y? Negative 200 meters. Looking for v naught, do I know theta? 37 degrees. Do I know t? 4 seconds. Do I know g?
Yeah.
Oh, I don't even need delta x for part A. Delta y will solve it for me. So can I solve that equation for v naught? In 2 shakes of a lamb's tail, right? So this is going to be delta y plus 1/2 g delta t squared divided by negative sine of theta times delta t. Can you read that? No. Sorry. Let's try that again. Watch this. We're going to divide by negative sine theta delta t. That's still not visible, is it? I was going to be real smart and make it red. Okay, so this is going to be V naught. So go ahead and calculate it. V naught is a delta y of negative 200 plus 1/2 9.8 meters per second squared times 4 seconds squared on the bottom goes negative sine of 37 degrees times 4 seconds. No, unfortunately we can't cancel out the t because there's no t in the delta y. So if I could factor out a delta t out of the top, I would be in duck soup. I could chop out the delta t. But because the delta y doesn't have a t in it, I have to stop there and just deal with the fact that this is going to be a little complicated. So, not an easy calculation, but I end up with 50.5 meters per second. So check it out. Make sure you get 50.5.
Oh, that's a plus.
Miss Smith, you okay out there? Okay. Allie, getting it? Jake, all's well. So forgive my messiness there, trying to get it all on the screen. You can blame Amanda. Just kidding, Amanda. We're not blaming you for anything. I'll get some phone calls. What'd you say?
No.
Okay. Question? Next part says, find the horizontal distance traveled by the package after it's released. Any ideas? Lucas?
What was the answer to the last part? The V naught?
I got 50.5 meters per second.
Okay.
Something's not coming out?
I got 60.8.
Oh, at least it's in the ballpark.
Yeah.
22.
Ellen, I want to roll yours out.
Run through it again. Make sure you square the time there. And make sure you put parentheses around the bottom. So you've got negative sine of 37 times 4 seconds. Make sure the 4 seconds doesn't end up inside the sign. You might want to reverse the order. Say negative 4 times the sine of 37 just to be sure. It's a button pushing problem. It's not a physics problem. Okay, so pretty clearly when you're doing part B, you're looking for delta x. So delta x is going to be V naught, which we found out to be 50.5, times the cosine of 37 degrees times 4 seconds. So it travels roughly 160 meters horizontally before hitting the ground. Okay? And V naught was 50.5.
I'm still in stout mode. That's why.
Oh, that would do it. Yep. If you've got radians on your calculator's brain, you're going to have some problems. You okay? All right, so here's what's going to happen. All the problems you do can be solved with the basic stuff you learned last year, but there's going to be like little tweaks here. Like, for example, that negative sign on that y velocity. So you have to do this with your eyes open. You know, look for these things that, oh, okay, I'm going to have to modify my equation this way from the way we did it before. So the first two examples we did totaled last year's problems, except for maybe that part about, you know, what angle does it hit the water. Future now, I'm going to throw some little tweaks and bear traps in there, and you're going to have to catch them. Okay? Any questions on this one? We've got one more to do. And then we're in pretty good shape. I'll even give you some time in class to work on the problems, since the other class, they use some time going over the problems. So I have to kind of be careful. There'll probably be a little bit of time, hopefully, toward the end. So second hour ends at 49, so hopefully, I
You
think,
got time.
yeah, we'll have some time. All right, we'll do a little circular motion, and then we'll slip into some problem mode here. All right. Wait, was that the last one? That may have been the last one. Hey, Evelyn. That's right. We had the Daredevil, which was different, and then we had this one, which was different. Okay, so those are our 4 examples. My apologies. Okay, next thing in this little chapter. There we go. Uniform circular motion. So it's kind of like part 3. Part 1 was motion in 2 and 3D. Part 2 was projectiles. Part 3, uniform circular motion.
You need 4. You need 4, because the last one was 3.
Yeah, no, last one was 3.
Last one was,
Oh.
we had motion, wasn't it?
Oh, we just started with, okay. How's that?
It works.
You can number them any way you like. Doesn't affect the content. Okay, now I performed this derivation last year, so maybe we can get away with not doing the derivation and just get into what the heck is going on. So let's say you've got an object that's moving in a circular path. Oh, look at that. And that object could be, let's say, a ball on a string. It could be a car going around a curve. It could be a planet orbiting a star. Question number 1, is it accelerating?
Yes.
Yes, it is. Why can you say it's accelerating? It's changing direction. So right now, if it's going clockwise, the direction of its velocity is always tangent to the curve. It's doing that. So at that moment, the object is moving in that direction, let's say. A tiny moment later, that velocity direction has changed, and because the direction has changed, that means the velocity itself has changed, technically. So it's accelerating. Okay, here's the deal. If you try to calculate the acceleration of this guy using the traditional delta V over delta T, it's not going to work. Because if you're using the magnitude of the velocity in 2 points, you're going to get a 0 on top, and you're going to get some time below, and you're going to say, oh, its acceleration is 0. So that delta V on top, this equation is actually true, but somehow you're going to have to include the direction in that delta V. So one way to do it would be to express the 2 velocities in unit vector notation. Okay, I hat, j hat. Then you notice, oh, the i's are changing, the j's are changing. The magnitude stays the same, but you've got some major things happening here. What we did last year is we set it up so that we looked at it at 2 different points and said, okay, this velocity is changing, and the angle between this velocity and this velocity is the same as the angle between these 2 radii. And we set up similar triangles. And in the end, we found out that the magnitude of the acceleration is v squared over r. Now, if you like, I can derive that from base principles and prove it to you. Or are you okay, because we did this last year, are you okay using that equation? Now, the thing to keep in mind here a couple of things. Uniform circular motion means constant speed. Okay, it's moving in a perfect circle at a constant speed. This acceleration is constantly changing as well, right? Because when the object's here at my first position, what's the direction of the acceleration? Toward the center of the circle. Right there. What's the direction of the acceleration? Towards the center of the circle. Did it change direction? Yeah. So it's tempting to say this is a constant acceleration, but it's not true. Just like it's not a constant velocity, it's not a constant acceleration either. The acceleration always points to the center of the circle. Okay. Are you okay with the acceleration being toward the center of the circle? Okay. If you have any problems with that, remember the little demo I did last year? I should have pulled it out again, but you take the little car that moves in a straight line, I attach a string to it, and I try to make it go around me. So in order for it to go around me, I have to pull on the string toward me. So a lot of people have this weird notion that the acceleration is toward the outside, which isn't so weird if you drive a car, because you feel as if stuff's being pulled toward the outside. So we have a misconception sometimes that the acceleration is to the outside. But what's really happening is that when there's a lack of force on the object, objects move in a straight line and appear, from our point of view, to be pulled out of the circle. If you want to stay in the circle, you got to have your seatbelt on, and it pulls you toward the center, keeps pulling you toward the center of the circle. Yes, ma'am?
Is it the same like if you're on a tire swing and you spin
Oh,
out?
yeah, absolutely the same.
Okay.
Okay.
Even if it's not a tire swing, but like just a regular swing, it's still the same? Like the acceleration is pointing in?
Well, in the tire swing case, you've got a horizontal circle, and the force that's keeping you moving in a circle is you hanging onto the tire, right?
Mm-hmm.
You apply a force to the tire applies a force to you. So you're helping to provide the centripetal force in that case. Now, if you're on a regular swing, going back and forth, that's a little more...
Spin it up.
Oh, you're spinning it?
Like, you know how, did you ever do it as a little kid when you sat in the swing and you spun around?
Oh,
and
yeah,
spun
so
all the way
you
up?
wind the chains around each
Yeah.
other? Yep,
And then you let go.
you bet. Now, down your center, there's no acceleration, no centripetal force, because you're just rotating.
Mm-hmm.
But like you stick your arms out, yeah, the force that accelerates your hand is the rest of your body. The attachments, the ligaments and so on, are keeping your hand moving in a circular path and applying a force which causes an acceleration toward the center. Yep, still works.
Mm-hmm.
So if you were like hanging on to like a big heavy rock while you're doing it, if you let go, that rock will just move in a straight line. What you're doing is you're applying a force to keep it from moving in a straight line, keep it moving in a circle. Okay? So this becomes clearer and clearer when we get into Newton's laws and so on. All right, so 2 examples. Let's see if I can get out of this mode here. When I do this, look at that. Okay, he's still in draw mode. Come on, baby. I want to go forward. There it goes. Just being a poop. All right. Got this car here. It's a 1994. This is getting old. I think I need a new slide here. It's a 1994 Probe GT. Worst name ever for a car. Why would you call a car a probe? I mean, it's like going to the doctor, right? Wow, these seats are uncomfortable. Anyways, it claims a lateral acceleration, that is when you go around a curve, a maximum acceleration of 0.87 Gs. So whenever you see G as a unit, it's not a unit. It's 0.87 times 9.8, where G is the standard acceleration due to gravity. This represents the maximum centripetal acceleration that can be obtained without skidding out of the circular path, because we don't want to skid or flip this thing. If the car is traveling at 40 meters per second, what is the minimum radius of curve that it can negotiate? Okay, assume a flat road. Unbanked and flat. All right. Go back to draw mode and see if we can do this. All right, our givens. You know what? Some days, it's not worth chewing through the leather straps in the morning. Okay, the acceleration that's allowed here is 0.87 times 9.80 meters per second squared. So if we wanted to, we could punch that out and figure out what acceleration is allowed. The speed of the car, or instantaneous velocity at any point in its path, 40 meters per second, which is really hauling. And they want to know R. So is this kind of a pretty straightforward problem?
Yeah.
Oh my gosh. So we're going to say A is V squared over R, solve for R. Okay? Now, these will get more complicated in later chapters when we add force and stuff. But for now, it's kind of like last year. You know, kind of got a real simple equation, you need to solve it. So if you're of the mind, we can calculate this radius, and it turns out we need to take 40 meters per second on top and square it. And on the bottom, we're going to take 87% of 9.80 meters per second squared. Okay, which is actually a pretty high acceleration for a passenger. But if you want to keep the acceleration at or below that, what's the radius? That's what I got, 190 meters, which is about 620 feet. That's a pretty wide curve, but we're moving really fast. So you don't want to, you know, like take a right-hand turn onto your street, you know, from Wilson, turn onto 40th Street, moving at 89 miles an hour because, yeah, you flipped that puppy. So it is going to be a big circle. So 190. Okay? So over 600 feet.
Okay.
Big circle. Next. Okay. You decide, you go to the carnival, you decide to ride the Vomitron, right? The Vomit Comet, or whatever you want to call it. The passengers travel at a constant speed in a horizontal circle with a radius of, helps to move this, I think. Oh, this is in draw mode. Oh, it still moves. Nice. Radius of, that didn't help. There we go. Radius of 5 meters. They make one complete circle in 4 seconds. What's the acceleration? Okay, this always drives the honors kids nuts. What do? They gave me a time. There's no t in the equation. I think I'm going to cry. Okay, the acceleration, v squared over r. So the short answer is, I got to figure out what v and r are. Oh, that was easy. I figured out what r was. What about v? Yay! So we've got this circle, and we know the radius, which means that we're going to 2
pi r.
Oh my god.
Finding the area.
Steven. It's been a long summer, hasn't it?
Yeah.
That's okay. I would have done that. I did that once. I was doing a physics, kind of a physics talk on supernova 1987A. And I got done, and the professor started asking me lots of questions, like, you know, what's the neutrino flux from this thing and so on. And you need to know the area of the sphere, you know, imaginary sphere around the star. So I did this 4/3 pi r cubed. And then everybody stops and looks at me like I'm stupid. And I go, oh crap, that's the volume. I need the area, in order to calculate the flux. And it's one of those things. It just pops out of your mouth, right? So anyways. So check it out. The velocity is going to be pi r squared over time, where if you want, believe it or not, hang on, before we get too far. Did I say pi r squared?
Yeah.
Dang it.
You wrote it right.
That one's your fault. No, that's my fault. Remember, the time it takes to go in one circle is called the period. It's a special time, capital T. So, if we want to, we could say it's 4 pi squared r squared over t squared divided by r. In other words, I took that v squared and I replaced it with that mess. So there's an advantage to that. Wow! That we end up with this cute equation, 4 pi squared r over t squared. Now if you read the book, you're actually going to see that equation there. I don't believe it's on your equation sheet, but it's not hard to come up with, right? It's a cute little equation. It's very useful, and all we're doing is replacing v with 2 pi r over t, or capital T. And that's kind of important, that it's the time for one revolution. Okay? If you know the time for one revolution, you got it. What if they tell you it's 5 revolutions per second? How are you going to find capital T? It's 1/5 of a second. So you just take the reciprocal, right? So if they tell you how many revolutions per second, you find the period by flipping. Frequency and period are the reciprocals of each other. Okay, so not too terrible. So, let's see. 4 pi times a radius of 5 meters times the period, 4 seconds, squared. Whatever the heck that is. I forgot to square it on the pi. Thank you. You are a scholar and a gentleman. Did you get 12 meters per second squared?
Yeah.
Okay. You're a scholar and a gentleman, and there are very few of us left. It's an old joke. All right. I'm tempted to move on to relative velocity, but my problem is your problem set is going to be way too big to do in one night. So I think what we'll do is for the last half hour or so, why don't you attack the problem set, and we'll get as many of these done as possible, because your job for tomorrow is to get these problems done by hook or by crook. So there's only 4 here for the second assignment, but on top there's another 5. So if you could get like the first 3 out of the way, now you've got a reasonable assignment. So the numbers are 13, 24, 25, 32, 109 for the projectile problems. And then I threw in 26, 34, 37, 120 for my lovely first hour class. And the hope is when they have a 0 hour Tuesday and then you have a 0 hour Thursday, there's a point where, you kind of come together. And so on Friday, we're all at the same point. So tomorrow, we'll finish up by dealing with relative motion very briefly. And then I'll give you the review for the test. Well, I just said them out loud, so I'm sure she quick wrote them down. But just in case, let's see.
Just looking
She's
at it.
gonna rewind it and be like,
Yeah, she's going to listen to it 5 times. So the problems just assigned because you didn't have an assignment, this would have been your assignment last night. But you weren't quite as far as the other guys who had a 0 hour. But now that you do have a 0 hour, you can catch up with them.
34, 37, 120. Almost said 102. Whew, that would have been bad.
Help her out with this systematic Make it sound like you're a good friend as well.
So 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you could get the first 3 or 4 done like right now, you will have a reasonable assignment to do for tonight.
Where are the books?
Oh, right here. I put them on the shelf here,
Jake, grab it.
so feel free.
Jake.
Okay, that's it for the video, Amanda. That was a long one. Call me if I can help. Peace out. Yeah, that was a 1 hour.